In this lesson, we're going to introduce and explain the last 5 derivation rules of sentential logic. All 5 of these rules require subderivations. Subderivations are when you temporarily introduce a new premise with a new scope line inside the main one to prove something that you can then bring out to the main scope line using one of the subderivation rules. Once you use that rule to add something back to the main scope line, the new premise you assumed is discharged and the subderivation is closed, meaning you can't use any of the lines from inside that subderivation anymore. We'll get into the details after we introduce the rules. The 5 subderivation rules are conditional introduction, biconditional introduction, disjunction elimination, and negation introduction and negation elimination. I'm going to explain these rules one at a time and give you examples of using them. Conditional introduction requires you to assume whatever you want as the antecedent of a new conditional. You draw a new scope line and then a line under the assumption to indicate that it's a premise you're introducing. Inside of the subderivation, you use the other rules we already have and the lines that you have above to derive the consequent of the conditional you're trying to get. Once you have the desired consequent on a line inside your subderivation, here represented by Q, you can end the subderivation and write down that conditional on the main scope line. The justifications for conditional introduction look like this. When you introduce the premise for the subderivation, you should indicate that it's a premise using P, and then write down which rule it's a premise for using the abbreviation. In this case, we do that horseshoe I for conditional introduction. On the line where you discharge that premise and actually use the rule beneath your subderivation, you write the abbreviation for the rule and then cite the entire subderivation by writing the number of the first line, then a hyphen, then the number of the last line. So here in this toy example is conditional introduction from lines 1 through 3. So now let's look at a problem. We're trying to derive if P then R from the premises if P then Q and if Q then R. We can do this using conditional introduction. Since we're trying to derive if P then R, we're going to assume that antecedent P and then try to get R inside our subderivation. So next I'm going to reiterate line 1. You can always reiterate inward or rightward further across scope lines. Technically, you could skip the reiteration and just cite line 1 here, but until you get confident with subderivations and learning when you are and are not allowed to use things, I recommend you use reiteration for keeping things straight. Remember, you can always reiterate inward, but you can't reiterate back out of subderivations, and we'll talk about that a little bit more later with other examples. So now I have P on line 3 and if P then Q on line 4. So I can use conditional elimination on line 5 to get Q. Since what I'm trying to get inside this subderivation is R, I'm also going to reiterate if Q then R from our premises onto line 6. And now we can use conditional elimination again to get R on line 7 from Q on line 5 and if Q then R on line 6. So now I've assumed P and used it and the other premises and our derivation rules to get R, to prove R inside that subderivation. So we could end that subderivation and go back to the main scope line with if P then R by conditional introduction, and we cite the whole subderivation from line 3 to line 7. Make sure you always cite the whole subderivation with this rule. It would be incorrect if you did something like just citing line 3, comma, line 7. You have to cite the whole subderivation, which we do using a hyphen. The next rule is biconditional introduction. Biconditional introduction starts with doing the exact same thing you do in conditional introduction. You assume the left side of the biconditional you want to prove, and then you derive the right side. But that's not where it ends. You have to do a second independent subderivation, assuming the right side of the biconditional, and then proving the left. We have to do two subderivations and prove it both directions because the biconditional is symmetrical. We do justification for the assumptions that start subderivations the exact same way as before. We label them as premises and then state the rule that we're assuming them that we want to use. It's an indication of what rule you're using that subderivation for. When we discharge the premises and use the rule on the last line, we have to cite both subderivations separately. In this case, it's lines 1 through 3 and lines 4 through 6. It's important that you cite them like this. It would be incorrect if you tried to cite them like one subderivation and just wrote 1 through 6. This rule requires two separate subderivations, so write the first one, a comma, and then the second one. So here's a problem. We need to prove A if and only if B from the premises if A then B and if B then A. This is quite a simple problem, but I just want you to see these rules in action. We start by assuming the left side of the biconditional. So on line 3, we introduce a new scope line with the premise A for biconditional introduction. Now we need to prove B inside this subderivation. So I'm going to reiterate A if A then B from line 1 on the next line. And on line 5, we can use conditional elimination to get B from lines 3 and 4. Now that first subderivation is done, so we can end it there, but biconditional introduction doesn't let us put anything on the main scope line yet. We have to prove it in the other direction. So we need to do another separate subderivation on the same level, assuming B where we prove A. We can't just reiterate A from line 3. This first subderivation is closed. So we can't use that assumption or anything inside that subderivation once we've exited that subderivation. This is always true. You can't cite lines or reiterate from a closed subderivation. You can't reiterate outward or leftward across scope lines. So now we need to do this subderivation without using anything from lines 3 through 5. Instead, we can reiterate the conditional from line 2 on line 7, and then do conditional elimination to get A on line 8. Now we've finished both subderivations, proving the conditional relationship is symmetrical. We can use the biconditional introduction rule on line 9 to write down A if and only if B. As I said before, we need to cite both subderivations separated by a comma. The next rule is disjunction elimination. The name elimination here is a little misleading. This rule doesn't mean you get rid of the disjunction and keep one of the disjuncts, though you can sometimes use it for that. Disjunction elimination allows you to derive anything that follows independently from both disjuncts. So to use this rule, you have to already have a sentence with a disjunction as a main connective on a previous line. Then you have to do two subderivations, one with each disjunct. Here R stands for any sentence you can prove follows independently from both disjuncts. Here's a silly example. Say it's true that either it'll rain tomorrow or it'll be really, really hot tomorrow. If it rains tomorrow, then it's a bad idea to work outside doing yard work. Also, if it's really, really hot tomorrow, it's a bad day to do yard work outside. So if we know it's either raining or really, really hot tomorrow, we can say we know it's a bad idea to do yard work outside tomorrow, even though we don't know which of the disjuncts are true, because it follows from both of them. The justification on the line where you discharge the premise using disjunction elimination requires you to cite three things. The line with the original disjunction, which in this example is line 1, the subderivation where you assume the first disjunct and prove whatever sentence you're going for, and the second subderivation with the second disjunct where you prove that same sentence. So now let's have a look at a problem. We want to derive J with the premises if G then J, if H then J, and G or H. So we're going to use disjunction elimination. We're going to start with a subderivation with G, our left disjunct from the disjunction on line 3. And we need to prove J. So we're going to reiterate if G then J from line 1. And now we can use conditional elimination to get J from lines 4 and 5. So now we've proved that J follows from G. Now we have to do the second subderivation to prove that J also follows from H. We can do this the same way we did the first one, doing it independently of that first subderivation. We reiterate if H then J from line 2, and then do conditional elimination from lines 7 and 9. After proving J follows independently from both G and H, we can go back to the main scope line and use disjunction elimination to write J on line 10. We need to cite line 3, with the original disjunction G or H, lines 4 through 6, that subderivation where we assumed G and proved J, and lines 7 through 9 where we assumed H and proved J. Okay, so we have two rules left, negation introduction and negation elimination. These rules are almost identical. They work the same way. The only difference is whether you're trying to put a negation on or take a negation off. With negation introduction, you're trying to derive a sentence that has a negation as the main connective. Your goal sentence has a negation as the main connective. So you, in the subderivation, assume that sentence without the negation on it and derive a contradiction. Deriving the contradiction proves that sentence is false. So you end the subderivation and can write down that sentence with the negation attached to the beginning. You take the assumed sentence and then write down the negated version on your main scope line. The goal with negation elimination is exactly the same. You're assuming something and then trying to derive a contradiction so that you can get the opposite back on the main scope line. The difference is that the sentence you're trying to get on the main scope line is not negated. So you assume that the sentence you're trying to get with adding a negation onto it. So here it's not the case that P. And then after you get the contradiction, you write down that sentence without the negation, eliminating that negation back on the main scope line. The justifications for negation introduction and negation elimination are really simple compared to the last rule we looked at. You use the abbreviation for the rule name, so the tilde and then either I or E, depending on whether you're adding a negation or removing one from the assumed sentence. And then you cite the entire derivation in which you get the contradiction. Let's look at a couple of examples so you can see this rule in action. So in our first one, we're going to try to derive it is not the case that P from the premises if P then Q, and it is not the case that Q. Since the sentence we're going for, our goal sentence, is negated, we're going to assume P without the negation as a premise for negation introduction. Now we need to try to get a contradiction inside this subderivation. Let's reiterate line 1. Now we can see that we have P and if P then Q. So on line 5, we can get Q by conditional elimination from lines 3 and 4. Now we can see we have a contradiction in here somewhere, right? We have Q on line 5, but we have not Q as a premise on line 2. However, we need to get that contradiction contained inside the subderivation. So we need to reiterate it's not the case that Q from line 2 onto line 6. Now we've got our contradiction in that subderivation. We can close the subderivation and write, it's not the case that P on line 7, citing the entire subderivation from our assumption on line 3 through line 6. This is negation introduction because we're introducing the negation onto the assumed sentence when we discharge it. Let's look at an elimination example. Here we're trying to derive the atomic sentence A by itself. So on the third line of this derivation, we need to assume the negation of A. This is an assumption from negation elimination because when we get that contradiction, we're going to take that negation off when we move back to the main scope line. We can see that from our new assumption and the biconditional on line 1, we can get B, and we also have the negation of B on line 2. So let's reiterate that conditional and get that contradiction on the inside. So now we can get B from biconditional elimination from lines 3 and 4 after we reiterated premise 1 to line 4. And then we can reiterate in, so we can reiterate not B from line 2, and we have that contradiction. Now on line 7, we eliminate the negation from our assumption and write A on the main scope line. Just like we did before, we cite the rule, which in this case is negation elimination, and then we cite the entire subderivation from lines 3 through 6. So those are the 6 subderivation rules. I know this lesson is long and contains a lot of information, and subderivations are generally hard to get started with. So check out these pages of the logic book, lesson 4 of the course manual, and the strategies for derivations in SD document available on the modules page. That document was made by a past TA of this course and really is an excellent resource. Just like the last video, I have 2 sets of recommended practice problems here. The first is filling in justifications for completed derivations, and the second is doing derivations on your own. I'll work through those last 3 derivation problems in the review video. In the next video lesson, we're going to look at more complicated problems involving subderivations, including when you have more than one subderivation at a time and have them nested inside each other. So go ahead and practice this before we move on to that.